In 1821, a German physicist pressed two different metals together, applied heat from a candle, and watched a compass needle move. He had just converted heat directly into electricity. No turbine, no steam, no moving parts. The device cost almost nothing. By the end of this video, you will discover exactly why it does not need such expensive parts and how to build one yourself today. The man behind this discovery was Thomas Johann Seebeck. He was working in his laboratory in Berlin when he joined a loop of bismuth and copper, heated one junction with a small flame, and observed something that should have changed the world. A compass needle sitting nearby deflected. Electricity was flowing through the metal loop. No battery, no chemical reaction, no mechanical input, just heat. The Prussian Academy of Sciences recorded the finding that same year. Seebeck himself misidentified the phenomenon, calling it thermomagnetic. It took the Danish physicist Hans Christian Ørsted to correct the interpretation. A temperature difference across two dissimilar metals produces a voltage. That is the Seebeck effect, and it was discovered over 200 years ago. 13 years later, in 1834, a French watchmaker named Jean-Charles Athanase Peltier ran an electrical current through a junction of bismuth and antimony and measured something unexpected. One side of the junction got hot, the other side got cold. He had discovered the exact reverse of Seebeck's effect. Together, these two breakthroughs prove something extraordinary. Heat and electricity are directly interchangeable through solid-state materials. No turbines, no generators, no moving parts of any kind. By the 1840s, the scientific community across Europe fully understood thermoelectric conversion. The physics was settled, but the Industrial Revolution had already placed its bet. Coal-fired steam engines were pouring money into the pockets of factory owners and railroad magnates. For every dollar spent researching thermoelectrics, roughly 200 went towards steam power development. The technology that could have decentralized electricity generation was quietly shelved, not because it failed, because it threatened the men who were already getting rich. But there was one government that did not forget. In fact, they deployed thousands of these devices across the most remote territory on Earth, and they did it in complete secrecy. To understand how thermoelectric generators actually work, picture what happens inside a small semiconductor chip about the size of a matchbox. The most common material used today is bismuth telluride. When one side of this chip touches something hot and the other side stays cool, electrons inside the material begin migrating from the hot side toward the cold side. That steady movement of charge carriers is electrical current. The temperature difference itself becomes the engine. The voltage from a single junction is tiny, measured in microvolts, but wire dozens of these junctions together in a series arrangement called a thermopile, and the voltages stack up into something genuinely useful. The efficiency of any thermoelectric material is measured by a dimensionless value scientists call ZT. For most of the 20th century, the best commercial materials hovered at a ZT of about 1.0, translating to roughly 5 to 8% conversion efficiency. A coal power plant operates at around 33%, so the number looks unimpressive. But this comparison deliberately hides something important. Thermoelectric generators do not compete with power plants. They harvest waste heat, energy that is currently being used for absolutely nothing. When your input cost is zero, even 5% efficiency means free electricity from energy already being thrown away. Now here is where this becomes practical. A standard Peltier module designated Tech 112706 is available worldwide for $3 to $5. Pair that chip with a $2 aluminum finned heat sink, a $1 tube of thermal compound, and a $2 boost converter circuit. You now have a functioning thermoelectric generator for $10. Set it on top of a wood stove with a temperature difference of 100 degrees Celsius, and it produces 2 to 4 watts of continuous power, enough to charge a smartphone, enough to run LED lighting all night, 2 to 4 watts from a $10 chip sitting on a stove. But what if an entire government had already used this exact technology to power critical infrastructure for 40 straight years? Starting in the 1950s, the Soviet Union manufactured thousands of thermoelectric generators under the military designation TGK-3. These compact devices were engineered to clamp directly onto ordinary kerosene lamps in rural homes scattered across Siberia. The kerosene flame provided the heat source on one side, and the brutal Siberian winter provided the cold sink on the other. Temperature differentials regularly exceeded 150 degrees Celsius. The output was enough electricity to power radio receivers in villages that had never seen a single power line. The entire program was never publicized in Western countries, but the Soviets were not alone. In 1977, engineers at NASA's Jet Propulsion Laboratory loaded Voyager 1 and Voyager 2 with radioisotope thermoelectric generators called RTGS. These generators use the radioactive decay heat of plutonium-238 on one side and the absolute cold of deep space on the other. That is the same Seebeck effect discovered in 1821. Today, Voyager 1 is more than 15 billion miles from Earth, the most distant human-made object in existence. Its thermoelectric generator is still producing electricity after 48 years. The Curiosity rover on Mars runs on this same technology. Every one of NASA's most critical, most distant missions depends entirely on thermoelectric generators. The quiet adoption extends further. Gentherm has built thermoelectric climate control systems into BMW and Ford vehicle seats since the early 2000s. The United States military field tested thermoelectric stoves in Afghanistan. In Japan, Komatsu reported successful energy recapture from steel furnace waste heat using thermoelectric recovery arrays as early as 2009. The Soviets powered radio networks with it. NASA trusts it beyond the edge of the solar system. The military deployed it in combat zones. Automakers embedded it in millions of vehicles. Which raises the real question, if it works everywhere else, why is it so difficult for you to use it in your own home? In most American states, connecting any power generation device to your home electrical system without a licensed electrician, a formal permit, and explicit utility company approval violates the National Electrical Code. Article 705 specifically governs interconnected electric power production sources. Even a 2-watt thermoelectric module wired into a household circuit without passing inspection technically falls outside code compliance. 35 American states deliver electricity through regulated monopolies. These utility companies receive a guaranteed rate of return on their infrastructure investments. Every watt a homeowner generates independently is a watt the utility cannot charge for. The Edison Electric Institute has poured over $100 million into lobbying since 2010 alone. Their own filings identify distributed generation as a direct financial threat to the utility business model. Look at what happened in Spain. In 2015, the Spanish government passed Royal Decree 900, imposing fees on any household generating its own electricity. Even families who never connected to the public grid were taxed for producing power on their own rooftops. The legislation was pushed by Spain's 3 dominant utility corporations. International outrage eventually forced a repeal in 2018, but the precedent was set. When a technology threatens utility revenue, regulation becomes a weapon. Then comes the efficiency argument. Thermoelectric generators, they say, only convert 5 to 8% of heat into electricity. The comparison is always against primary generation systems, but this comparison is fundamentally dishonest. Data published by Lawrence Livermore National Laboratory reveals that roughly 67% of all primary energy consumed in the United States each year is rejected as waste heat. A 5% recovery of even a fraction of that enormous waste stream represents tens of gigawatts of electrical capacity that currently does not exist. They said the technology does not work. They built regulatory walls around it. But there is one thing no regulation on Earth can prevent: the build itself. Here is exactly what you need. 1 TEC 112706 Peltier module, $3 to $5. 1 aluminum finned heat sink, $2. 1 tube of thermal compound, $1. 1 MT3608 DC to DC boost converter, about $2. Total investment under $10. Clamp the hot side of the module against any consistent heat source. Attach the cold side to the finned heatsink and expose it to open air. Run the output through the boost converter and you get clean, stable 5-volt power through a USB connection. Researcher Paul Shortino at the University of Nevada in Reno mounted a 4-module thermoelectric array onto a standard residential wood stove. The system consistently delivered 10 to 15 watts of continuous electricity. That was enough to power an entire off-grid LED lighting system and enough to charge a laptop computer. Families in rural cabins ran lights and radios powered entirely by the same stove they already used to heat their homes. This is not about disconnecting from the electrical grid. This is about opening your eyes to energy that already exists inside your own home and is being wasted every single day. A $10 thermoelectric module captures that wasted energy and converts it into usable electricity, power that no utility company can meter. Look at what we have uncovered together. A discovery made in 1821, a technology validated across 2 full centuries, Soviet kerosene-powered radio networks, NASA spacecraft still transmitting after nearly 5 decades, military field stoves, automotive climate systems in millions of vehicles, industrial heat recovery plants, all built on one elegant principle. A temperature difference across 2 materials generates electricity. This technology was never lost because it stopped working. It was buried because it threatened the centralized energy model that funnels billions of dollars to a small number of corporations every single year. But the physics cannot be unlearned. The components cannot be uninvented. And the knowledge you now carry cannot be taken away from you. 200 years of science, validated at every level from a candlelit laboratory in Prussia to the black void beyond Neptune, is now yours. There is something satisfying about pulling electricity from heat that is just going to disappear anyway. A wood stove radiates into the room, an exhaust pipe dumps thermal energy into the air, a furnace sends warmth straight up the flue, all of it energy bleeding off into nothing. Thermoelectric generators sit at that boundary and skim a little power off the top. The physics behind this is the Seebeck effect. Run a temperature gradient across certain semiconductor junctions and electrons start moving. Voltage appears. The same Peltier modules people buy for cooling electronics work in reverse. Instead of pumping heat when you apply power, they generate power when heat flows through them on its own. The T-Swan 12706 is everywhere. 40 millimeters square, a few dollars, ceramic plates sandwiching semiconductor elements. The printing on one face indicates what would be the cold side in cooling mode, which means for generation you want heat hitting the blank face while the labeled side stays bolted to a heat sink. Beyond the module itself, an aluminum finned heat sink slightly larger than the module footprint, thermal compound, and an MT3608 boost converter for voltage regulation. Wire, solder, basic tools, total cost runs maybe $10 to $15 depending on what is already in the parts drawer. Output lives and dies by thermal contact. Air gaps are the enemy. Every pocket of trapped air acts as insulation and chokes off the temperature differential that drives the whole system. Clean both faces with isopropyl alcohol, check for scratches, then spread thermal compound thin enough to be just opaque. Both sides of the module get this treatment. The heatsink needs sustained pressure against the cold face. Mounting hardware beats hope and gravity. If the fins are passive, point them upward so convection can actually do its job. Hot air rises, pulls cooler air in from below, and keeps the cycle moving. Flat surfaces like stovetops are easy. The module goes down and the heat sink rides on top. Curved surfaces like exhaust pipes need an intermediary, an aluminum adapter plate shaped to the curve on one side and flat on the other, clamped in place. Hose clamps work fine. A single module under real-world conditions puts out somewhere between 1 and 4 volts, depending on how much temperature differential exists across it. That is not directly useful for most electronics expecting stable 5-volt input, so the boost converter bridges the gap. The MT3608 takes the variable trickle from the module and steps it up to whatever the potentiometer is set to. Dial it in with a multimeter once things reach operating temperature. One module is a proof of concept. Multiple modules are a system. Series wiring adds voltages. 4 modules, each producing 2 volts, yield 8 volts combined. Parallel wiring adds current capacity while maintaining voltage. A copper spreader plate on the hot side helps distribute heat evenly across module faces. Active cooling, a small fan on the heat sink, often doubles or triples output compared to passive convection. Ceramic fiber insulation wrapped around the hot side keeps thermal energy from escaping sideways before it can flow through the semiconductor junctions. The hot face tolerates around 200 degrees Celsius before permanent damage sets in. Running without a heat sink attached invites thermal runaway and a dead module. Keep wiring clear of heat sources. The hot side of an operating system will burn skin on contact. Anything feeding into lithium battery charging needs proper charge control. Boost converters alone will not prevent overcharging. Wood stoves already running in winter. Furnace exhausts. Any heat source that operates regardless of whether power comes out the other end. The electricity is incidental to whatever the primary function is, staying warm, cooking, running an engine. Thermoelectric harvesting just intercepts some of that outbound energy before it dissipates. No sun required, no grid connection, just heat differential and a place to dump the cold side.